Hey there, guys. I'm going to go through topic 2.3, 2.5, or more specifically, we're just going to talk about curved mirrors and lenses. Okay. So again, I'm combining two lessons. This is a really fun section to do in the class. We do a lot of demonstrations, not so much stuff that you have to do labs on or whatnot. We watch some fun videos and we play with mirrors and spoons and lenses and projectors and things like that. Unfortunately, not sure how we're going to do that from here, but I'll try to come up with some creative ideas that you can do at home. Maybe not necessarily for homework, but something that you can do. We'll see. Okay, so we're going to talk about curved mirrors first. Okay, we've already, we've all seen curved mirrors before. This one right up here, I've got a nice little picture of it. You probably have these in your home. Okay, this is a concave mirror. You can see it curves in kind of like a cave, okay, or like a bowl. Concave mirrors form images that appear to be closer than they actually are. And this is actually very, very useful because it can also reflect a large amount of light from a specific area. Okay, they're good at collecting light because all the light comes in from whatever source, and as you can see from right here, it bends. Okay, or though it doesn't bend, but it reflects because it's curved. They're not all reflecting parallel like a plane mirror. They're reflecting all to a point. Okay, so it all comes and collects at this single point. Okay, and this is why they're ideal for reflecting telescopes. So if you remember, we talked about two types of telescopes, reflecting and refracting telescopes. Reflecting telescopes use a combination of this mirror, a lens, and also a plane mirror. And they'll take light from far, far off places like a star far, far away. And all that light from that star will go through the telescope, go through the eyepiece, hit the curved mirror, and then it all bends to this little focal point. Okay. And so it's collecting the light from far, far away sources. So it makes it, even if it's a really dim light, it's collecting the light from it so it actually intensifies or magnifies it. So you can see it better. Okay. When parallel rays approach the curved surface, they strike at different points on the curve, and each one will reflect slightly in a different direction. Now, in the classroom, students would say, "Well, this doesn't agree, or this disproves the law of reflection." That's not true. Okay, because remember, the law of reflection is always the light reflecting relative to the normal. So you have to imagine here an imaginary line and an imaginary line that's perpendicular to this surface here. So the normal itself ends up by curving out. So the angle ends up by being the same. The angle of incidence and the angle of reflection. Okay, so these light rays all converge and come together to something that's called the focal point. Okay, so the focal point is this point right here where they all meet and all the light rays meet after being reflected by a mirror. Okay, and that's it right there. With concave mirrors, the focal point is in front of the mirror. So here's the mirror. The focal point is always right in front of it. Okay, so imagine if hypothetically, imagine you were stuck on a desert a deserted island, a desert island, right? Kind of like Gilligan's Island. Ask your parents about that. Okay, so you're stuck on an island, and all you had was a mirror like this. Okay, this mirror could actually help save your life, right? Because all the light rays come in and hit, and they meet at this certain point. All those light rays meet at this focal point. So, do you think that'd be pretty useful? Yeah, that'd be very, very useful because all these light rays, especially if it's coming from the sun, remember the ray diagram just represents sort of a model. All of these light rays end up by coming to this certain point, and because it's coming from the sun, the intensity of those light rays would be huge. And because they'd be so huge, it could potentially start a fire. So you could go and keep yourselves warm, things like that. Okay. We're going to be talking about a property of lenses that does something very similar. I'm going to pause this here and go grab a prop. I'll be right back. Okay, so I'm back. So some of you may remember seeing this thing in my classroom. Some of you said it's a satellite dish and whatnot. It's not a satellite dish. Okay, what this is a concave mirror, and we've got a little tiny little pot in the corner here. The relationship between this pot and the mirror is, as you would guess, the focal point. So all the light rays coming in from the sun would come, bounce, or hit the mirror, and then they'd all go and bounce back at this point. The purpose of this is that as a model, it's called a solar furnace, and it's sort of a model just to show how the heat from the sun could go and heat up something in this little pot. I've had Miss Fee take this out in the past, and she tested it in the schoolyard, and they actually took some snow and they were able to melt the snow. We may demo that here. When I actually brought this home from OLQP, when I left OLQP to come here, I had this in the back of my car, and I just threw it up onto the side and just driving home. Like OLQP is not very far from my home, probably about 10 minutes. When I got home, I noticed smoke in the back of my car, and this had actually went onto the side of the van. The sun was shining through the window. It actually melted the van, so kind of scary. So yeah, so that's what happens when the light rays come from another source. Now, imagine that instead of this being a focal point, we ended up by putting a flashlight, or sorry, we put a light bulb right here. If we put a light bulb right here, okay, the light would be shining out from all different directions, but these light rays here would end up by hitting the mirror. If we were to switch the direction of all these arrows, because the ray diagram, this was the light source, the light bulbs would be hitting here and coming straight out here, hitting here, coming straight out here, hitting here, and then bouncing right back. It would be all over the place, okay? This is also a very, very useful application for curved mirrors, okay? So by reversing the arrows, like you can see here, by reversing by reversing the arrows, you can see that the light rays would end up by leaving in a parallel fashion. This is how flashlights or the headlights of your car actually work. So the flashlight, the light bulb, is actually right at the focal point. So the light rays are bouncing all over the place, but a lot of them are hitting that mirror. And because it's coming from the focal point, a lot of them are hitting the mirror and they're coming out in a parallel fashion straight in front of you. Very, very important for cars, very, very important for flashlights, all those types of things. Okay, they can also be used for security devices, telescopes, and cosmetic mirrors. One really big one here. You guys probably have these something like this at home. Okay, got a really big one here. My wife has one in the bathroom. It's a cosmetic mirror. You guys probably have them at home. You know, you put your eyeliner on and whatnot. Okay, you can see my image. Maybe you can see it. Let's make it nice and bigger. Let's see if this works. Okay, you can see my image. It gets really, really large. Like, oh, massive, right? You guys have this. You guys probably have the same thing at home. You probably have the exact same thing at home in your bathroom. Okay, so something to keep in mind. You can go play with it. If you didn't have one, another thing you could use is a spoon, the surface of the spoon. Okay, concave mirrors also form images. Okay, the image formed from a concave mirror depends on how far the object is from the focal point. So we can actually project images with the concave mirror. Okay, and if the object is just past the focal point, it's upside down and large. Okay, so upside down image. We saw this before. Okay, think back to the pinhole camera. So here we have a beautiful picture from your textbook. I copied it right out of your textbook of the concave mirror. Here's the focal point. Here's the object. If the object was far or was in between, sorry, if the object was past here, the image or the projected image would actually be upside down. Now, going back to my mirror, this is one of the fun things we would be doing in class. If I actually take a look at something in this mirror, okay, right now I'm in between the focal point and the mirror. So my face is right over here. If I was to go and move myself out here, everything in the mirror would actually appear upside down. Okay. The image of the mirror, the image formed by the mirror depends on how far the object is from the focal point. Again, like we just said, if the object is far past the focal point, it'll be very small and upside down. So if the object was way over here, if I was to take this and move it way, way, way past over here, I would look smaller and I would be upside down. But here's where the useful part of it is. If the image or the object is between the focal point and the mirror, like I just demonstrated right here, the object or the image is actually enlarged. And this is where those mirrors become very, very useful for doing your makeup or squeezing those zits and those blackheads or whatever you guys do with these these cosmetic mirrors. The other type of mirror is a convex mirror. Okay, convex mirror has a reflecting surface that curves outward like the back of a spoon. Okay? It does the opposite of a concave mirror. Instead of collecting light, it diverges light into all these different directions that get reflected off. If you look into a convex mirror, it appears like the image is originated from a smaller point behind the mirror. So the focal point is actually a virtual focal point behind the mirror. Convex mirrors reflect parallel rays of light all over the place, as though the focal point was behind. Okay, and we've all seen these as well, because the objects on these convex mirrors. On the convex mirrors on the sides of cars, they'll have the little warning that says objects appear closer than they actually are. If you've ever watched Jurassic Park, the first one, not the new ones, but when the big T-Rex is chasing after them after he eats the guy that was on the toilet, and they're chasing after and they're driving, and Laura Dern is screaming hysterically, and she looks in the rearview mirror or in the side mirror, and she sees the big giant T-Rex open up his mouth and growl, and like it's terrifying, it's so scary, and it's so close in the mirror, and then right underneath it says objects are actually closer than they appear. So that T-Rex was actually closer than when it actually appeared in the mirror, and is freaking them all out. Kind of a funny point of the movie. So we've seen those convex mirrors in on the side mirrors of cars. We also see them in school. We see them in stores. Okay, so this is a concave or convex mirror, and you can sort of see my reflection in the messy office. You see these typically in like drugstores or Safeway, sort of as a security matter to make sure that people are not in the aisles putting things in their pockets and whatnot. It gives a wide view so you can see a big open area. Okay, right here's a couple of videos. They won't play because it's YouTube, and I'm putting this on YouTube. But I will put links to these videos. They're really useful videos, so please make sure you watch them. They're not too long. One is a teacher that actually teaches something very similar. He has the same props I do, and the other one, it's a really cool demonstration of a pendulum with a concave mirror. Definitely recommend you guys watch this. Now we go to lenses. Okay, so when we're talking about lenses, we're talking about like glasses lenses, magnifying glass lenses, those lenses that we had in the Light Up Your Life demonstration. Okay, and you're going to find that the lenses do something very similar to the curved mirrors. Okay, so a lens is a curved piece of glass or transparent material, plastic, like these magnifying glasses. Okay, when the light rays pass through them, they get refracted, causing the rays to bend. Okay, so we just talked about curved mirrors that reflect the light, causing the rays to go to a certain location. Lenses do something very similar, but they allow the light through, and then the light bends. The first lens we're going to talk about is the concave lens, or the double concave lens, and these lenses are thinner, is thinner and fatter in the middle. Sorry, is thinner and flatter in the middle than on the edges. Okay, light passing through the thicker, more curved areas of the lens bend more than the light passing through the thinner areas, causing the light to spread out and diverge. And here's a beautiful picture. Okay, so we saw this when we did the Light Up Your Life demonstration. The light rays, when we were looking at the graph paper, it looked like the images were actually, or the graph paper was actually getting smaller. Little squares were actually getting a little smaller, and in some cases, didn't really see it on my video, it looks like the lines start to curve a little bit. That's what the concave lenses do. The double convex lenses are a lot more useful, and they're a lot more fun to play with. The double convex lens is thicker in the middle and than it is around the edges. Here is a double convex lens, okay, magnifying glasses. Okay, this causes the light to come together to a focal point or converge, just like this. Okay, so if you take a look here, the light rays come through and then it all bends again to a focal point. This is very similar to the concave mirror. So it does the exact same thing with the light rays, almost exact same thing, but with the light rays as it does with the concave mirror. Okay, if we go back here, this one does similar. It works similarly to the convex lens, where the light rays, convex mirror, where the light rays bend off all over the place. So again, you're stuck on a desert island. One of these things, sure, you can help you use, find clues, find really small things, but this can also converge all the light from the sun to a certain point so that you could start a fire and stay warm, cook some food, have a good time. Okay, lenses are useful optical devices, as are mirrors. Okay, eyeglasses have been made from lenses since the 13th century. So these glasses have been using lenses since long before we were born to help improve our vision. And we're going to go more about that in topic 4. Convex lens refracts the light rays from an object so it can be focused. And different size lenses converge the rays to different distances, enabling corrections to be made to focal points. That's how we correct vision. We're going to worry about that a little bit later, though. But here's exactly how it does that. So here we have a fat lens. So if you see the fat lens, it bends the light rays a lot at a more of an angle, so that the focal point is closer to the lens. If the focal point didn't have to be closer to the lens, it would bend the light rays. You'd use a thinner lens, and it would bend the light rays to a different point. For vision, what we want to do, and you're going to learn about this next unit, is you want to have the focal point right on the back of your eye, your retina. Well, sometimes that doesn't happen with certain vision problems. The focal point ends up by being back here or in front. So you'd use lenses to move that focal point so it's right onto the back of the eye, which is called the retina. Okay. Light from the left portion of the object is directed to the right, and the light from the top is directed to the bottom. Hence, we end up by getting what kind of image? Okay, it's an inverted image. It flips it up upside down. This is just like overhead projectors and film projectors. They actually do this. Remember a long time ago, before we got stuck being at home and we were able to go see these things called the movies, we were able to go to the theater and whatnot, and you can go and watch on a big screen, have popcorn, be with your friends, sit very close, not 2 meters away. They showed these videos using projectors. Next time you guys go, or if you have a projector at home, take a look at the projector itself. Take a look behind you in the projection room and see if you can actually see the image. You can actually see the image on the screen as it's getting projected onto the big screen, and that image is actually upside down. It's actually upside down and inverted. It's really cool. Very similar to our pinhole camera that we did last week. And you can actually do this with a magnifying glass. This is one of the fun things we would have been doing in the classroom. If you have one of these, do it, okay? You can just simply take a candle, okay? And using a magnifying glass, okay, adjust the candle, and you can actually project a real image on the wall. So it's actually like a projector. Okay, I'm also going to show you guys a video. I'll put a link onto a YouTube video where you can use one of these. This actually was from the dollar store, I believe, where you can actually make your own projector for your cell phone. So image formation with a convex lens. The formation of an image with a double convex lens depends on where the object is placed, okay, and the orientation of the light source. Okay, here's a pretty picture, and here's another pretty picture showing the focal point, how the light converges, and again, very similar. The light rays can bounce straight out, or you can have them move to a focal point. Not super important. And right here is a link to a video. It shows very similar to the images with the mirrors, where you can have an object, if the focal point is right here, you can actually project a small upside down image over here, and then if you move it closer, the image the image itself still upside down, it gets bigger. And then if you actually move it in between the focal point, you can actually get a virtual image, an image that's not actually there, kind of like a hologram. So it would be on both sides. We would have been doing this as well. It's kind of cool where you end up by getting an image where it looks like you poke your finger through it. It's called like a hologram. But don't worry about that. That stuff is like high school level. We're not going to be playing too much with it for grade 8, but it's kind of important to know. That is it. So I will be posting a video. I think I'm going to go outside. I'm going to try the solar furnace, compare it to the magnifying glass, maybe pose a few questions for you guys. Other than that, it's probably going to be application questions. I don't think I have a lab or anything like that for you. I might create some sort of Flipgrid assignment. We'll see how it goes. But for the time being, that is it. That's the end of topic 2 for the light and optics unit. I will be posting a quiz for you guys. Again, open book quiz because homeschooling, etc. And we'll go from there. I hope this one was okay. This would have been so much fun in the classroom. It usually takes about 3 days to get through it with all the demonstrations and fun things that we do, but so it's such as life. All right, have a great day, and see you guys.